All righty. We'll get started in one more second. All righty, everyone. Welcome to the broadcast. I'm Sam Charrington, host of the TWIML AI podcast. And today I am super excited to be joined by an amazing panel to take on the topic of programming languages for machine learning. Research suggests that the natural languages we speak can influence the way we think and approach the world around us. The same concept applies to programming, with different languages encouraging fundamentally different ways to attack given problems. In machine learning and AI, we spend a ton of time talking about high-level machine learning and deep learning frameworks and toolkits. And we also see plenty of Python versus R language flame war style discussions. What we're hoping to do today, though, is a bit different, a thoughtful, comparative exploration of different programming language options for data scientists and machine learning engineers. Because there's no best programming language for every job, today is more about exploring why each language is worthy of your consideration and the new perspectives that they offer. I suspect and hope we'll also hear a bit about each language's shortcomings and challenges as well. The point is to learn about how each of these languages can help us better express our problems and solutions, and hopefully even provide some ways of thinking about what new languages that aren't represented here might have to offer. Before I introduce our panelists, I'd like to send a huge thanks to our friends at IBM for sponsoring this discussion. IBM is committed to educating and supporting data scientists and bringing them together to overcome technical, societal, and career challenges. Through the IBM Data Science Community site, which has over 10,000 members, they provide a place for data scientists to collaborate, share knowledge, and support one another. IBM's Data Science Community site is a great place to connect with other data scientists and to find information and resources to support your career. Visit twimlai.com/IBM community to join, and while you're there, get a free month of select IBM programs on Coursera. At this point, I'd like to quickly introduce our panel, and then when we start the program, they'll have an opportunity to introduce themselves more fully, but please join me in welcoming them. Representing Clojure, we have Chris Nuernberger, Managing Partner at TechAscent LLC. Representing JavaScript, we've got Burak Kanber, CTO at Tidal Labs. Representing Julia, we've got Huda Nassar of Stanford University. Robert Osazuwa Ness of AltDeep.ai will be representing probabilistic programming. Catherine Nelson at Concur Labs will be representing Python. Gabriela de Queiroz will be representing R. She's a senior machine learning manager at IBM and founder of AI Exclusive and R Ladies. And Avi Bryant, who's an active participant in the Scala community, will be representing Scala. And Chris Lattner of Sci5 will be representing Swift. Each of our panelists will have 4 to 5 minutes to present on the language they're representing. Following these presentations, we'll be opening up the floor for discussion and audience questions, and it's my sincere hope that you, the audience, will drive a good part of our discussion today. We'll have about 40 minutes for that segment of the event, so please be sure to route your questions via the YouTube chat so that I can relay them to our panelists. Finally, we are really looking forward to bringing you more discussions like this on a wide range of topics. To be notified about those, subscribe to our newsletter at twimlai.com/newsletter. So let's get started. Up first, representing Clojure, will be Chris Nuernberger.
Thank you, Sam, for the introduction. I'm really honored to be here. So my background originally was 3D graphics back in around year 2000. and then some GIS, and then 3D graphics, this time through a lens of C# and C++ CLI, a language. C++ CLI I still think is a language that has things to teach us now. And I worked a long time at NVIDIA and really got into high performance C++ and GPU programming and really advanced graphics. After that, I was a founding member of a machine learning startup that worked in Clojure. And my path to Clojure was when I was doing C# apps, I got RSI. And I decided I wanted languages with the highest possible leverage. And the reasoning was, metaprogramming gives you higher leverage than programming, of course. And so I got into Lisps, and that led me to Clojure. So I have a background in high performance computing. I know quite a bit about machine learning and deep learning, and I work with amazing people who know all the pieces that I don't. We really like Clojure because what we found doing machine learning was that it was a lot of data cleaning and data processing and getting random data from random places into a format where it even made sense to hand it to any sort of simple statistical modeling system, whether it be XGBoost or whatever. And Clojure is really concise, and it's got a very good REPL. So when you're in the, let me back up. A REPL is a way that you can see the data and the code that you're working with visually. When you're working with data in exploratory phase, it is really useful to see exactly what you're doing and to see a lot of aspects of the data. And modeling programs functionally and modeling programs as transformations between one data structure to another data structure, we've found to be a very easy way to reason about what's happening. It's easy to debug because we can see what's in the data structures at any point we want through the REPL. And we find it just really concise to get a lot of things done. That kind of mixed quite a few things together, but we're strong believers in functional programming. And we find that Clojure gives us some of the best access to functional programming that we think has ever been designed. Moving down, I've also authored a library called libpython_clj, which allowed us to embed Python in the JVM. So we're not beholden to the libraries that only exist on the JVM, which would cut out most or a great number of advanced machine learning libraries. And we've authored an ML stack that includes a data frame library that has comparable performance to Pandas or R's data table. So I think Clojure fits really well in a heterogeneous machine learning system in that it is the most stable of all the languages you're talking about. And a lot of Clojure libraries haven't been touched for 5 years or 6 years or 8 years. We don't have to change our libraries when our compiler changes. We don't have to change things a lot. We still run on JVMs 7 and 6 and all sorts of other stuff. So it has a very stable foundation. That was one of its designers' main goals. But aside from that, it is a Lisp. It allows me to do to extend the compiler while I'm programming on my problem. So I have very explicit control over the bytecode that it generates, which is not something that I find very easy to do other than in languages like C++. That is it. We've had great success for many clients. We've built weather systems. We've built lots of apps. We've built all manner of things that involve big data, facial rec with deep learning. So Clojure is a small language, but it to use a boxing term, it punches well above its weight. The drawback is it's a niche language, and it's also a language that takes a long time to learn. So it looks very simple, and you can do a lot with very little with it, but you do need to spend time learning the language. It's a very high leverage language. I think it suits really well when you're more at the medium to maybe medium to advanced stage of your programming career. And if you are in that stage and you're in an area where you don't need the absolute best performance in the world, Clojure often offers the lowest code pathway to getting something complex done. And that is all I have to say about Clojure for now. I'll open up.
All righty. Thanks so much, Chris. Next up, we've got Burak Kanber representing JavaScript.
Hey, Thank you, Sam. And I really appreciate the excuse to wear a collared shirt today. So I'm happy to be here. My story is I started in machine learning back before Node.js was a thing. I was working in PHP at the time, and I got a lot of hate for that. How dare you attempt machine learning in PHP? I thought that was pretty silly. In my mind, any clever person can write an algorithm in any language. It's a technical skill, like any other technical skill, and it requires time and effort and practice, but there's no magic about it. So I set out to prove to the world that machine learning can and should be accessible to programmers in any language or environment. So I picked, at the time, the most universally reviled language I could find, which happened to be JavaScript. And I started blogging about machine learning. And I may have started it just a little bit ironically, but I quickly fell in love with the fact that you can combine the algorithm and a visualization and exploration of data and interactivity in one nice, neat little package deployable to the web. So that's the first important thing I have to say about machine learning in JavaScript. It's the educational aspect. I think if you're a full-time JavaScript developer and you have 2 kids at home to take care of, and you're interested in machine learning, it's tough for you to jump right in, not only to machine learning, but also into the Python or R communities and those ecosystems and environments all at the same time. That's a pretty high barrier to entry. So I think lowering that barrier would help us tap into the wider JavaScript community and, in order to train up the next generation of machine learning practitioners. So I love JavaScript for the educational aspect. I'm not really saying anything new here. I'm really just saying that education is good, but it's still not happening enough. And I think that's a pity. JavaScript, the language, is actually pretty nice for machine learning. As Chris said, about 80% of what we do is utility code, loading data, moving it around, batch training, things like that. And the async and event loop model that JavaScript follows as a language makes a lot of sense there. And more practically, personally, I want to see better support for machine learning on all platforms. I like single, simple stacks. If your whole stack is in PHP or it's in Ruby or JavaScript, you shouldn't have to drop into a microservice to do the common industrial machine learning tasks that most businesses need. So I say that's probably the biggest downside of machine learning in JavaScript today. There's a lot of innovative stuff happening, especially in the neural network realm. GPU acceleration is somewhat new to JavaScript, right? But there still is not a lot of support for the less sexy, more industrial machine learning applications, the types that businesses use on a daily basis. And on top of that, you can certainly criticize Node.js as a runtime for machine learning models. But I think what I'm most interested in is where this goes in the next 5 to 10 years. Forgetting about Node.js as a runtime, think about how interesting the browser is as a runtime and a medium. It's incredibly portable. It abstracts away not only the user's hardware, but also the user's operating system. It interacts with the network. It interacts with user media and devices. It runs on mobile. It's sandboxed. It talks to the GPU. It speaks WebAssembly. It's multi-threaded. So I'm really interested to see what the next generation of machine learning engineers can do with browsers as a runtime, portable JavaScript applications for distributed model training. I think there's a lot that JavaScript can give us just from a technical perspective that we're not really scratching the surface on yet. And of course, being close to the browser means we're very close to the user itself. As our edge devices, mobile devices and maybe even IoT devices really improve over the next 10 years, I'm interested to see what we do with machine learning right in the media loop, or machine learning on your edge devices for security or privacy purposes. There's a lot I think we need to explore there. And that's all very compelling to me. So ultimately, I think JavaScript has a ton of potential. We're not seeing a lot of it today as things stand. But I do think we should take a closer look at JavaScript And not just how the language helps us, but how the browser environment and also the talent pool that's just sitting there waiting to learn machine learning and become practitioners. I think if we start paying attention to those things, we'll be able to do a lot of exciting things in the next 5 to 10 years. And that's it for me.
All righty. Thanks so much, Burak. Next up, representing the Julia language is Huda Nassar.
Hi, thank you, Sam. I think I might have a slide there. All right, I guess I'll get started with talking while the slide is being pulled out. So yeah, my name is Huda Nassar. I initially got interested in Julia. Well, actually, my PhD advisor, who's probably watching right now, sent me information about Julia and told me about Julia. And my very first experience with it was porting some code that was taking in my previous pipeline about a day or two to actually finish running. And then I rewrote some of the main components of it in Julia, and it just was super fast. And since that instance, I was immediately hooked to the language. So now that my slide is up, I'm just going to go through the components that I have here in the slide. So basically, I just took a screenshot of if you go to www.julialang.org, you will see these very first 6 components of the language right at the front page. And they're, yes, a selling point, but they're also the reason, one of the biggest reasons people switch to Julia is its speed. So you see the very first component there is that Julia is fast. And I do have a screenshot here from another benchmark on also the Julia Lang website, where you can see benchmarks on different types of or different kinds of problems where Julia is compared to other languages. So speed is certainly one of the biggest selling points, and it certainly was the main selling point for me personally. The other component is multiple dispatch. And one thing about multiple dispatch is we often think of oh, we have a generic programming or generic function or method, and then we have new types. And then basically in Julia, all you have to do is, if you have to specialize a certain thing in your function, you just have to specialize, for instance, for a new type, if you need it, and then the type is just often just ready to be plugged in whatever code you already had. The main one thing I really like about is actually the inverse of this problem, also related to multiple dispatch, where you have usually a generic type, a type that already existed, but you also want to add functionality to it. And usually say, if you have a classes type of programming or software development, you usually want to either want to create a subtype or create there's some more work you have to do around it to get your new functionality working. But here in Julia, you can just basically use the code itself. There's essentially there's not a lot of work that you have to do when you have to introduce a new type. So these are the 2 main components of multiple dispatch. I think these influence the code resharing and code reuse drastically, because essentially what happens is all the code ends up in essentially one place. Most of it is on GitHub, and basically you have to do a lot less copying and pasting and creating your own version of the problem or your own kind of sub module. So it really facilitates the collaboration process. Another thing I really like, this idea of dynamic typing and static typing, which are kind of intertwined together, which are these second 2 components here, and dynamic and optionally type. And the reason I really like that is often, especially in machine learning or data science, a lot of times what we end up doing is basically write a certain pipeline or a certain piece of code. And initially we don't worry too much about the typing, and we would just want to see whatever we're implementing to see if it's working. And this essentially removes one component from the software development process, which makes it easier from a developing perspective. But at the same time, it's really easy to type things as well. And actually, you would be if you actually know the types, it is recommended that you add the types. And being a typed language actually is one of my favorite things about Julia. But this intertwining between the 2 things, it's what's key here. that you can go back and forth between the two things. Finally, the two things, open source. I mean, open source like is a great, I think everyone would agree that we all like open source. So yeah, it's cool that it's open source. You can just go look at the source code whenever you're having trouble with something or you want to take a look at certain implementation. And finally, the easy to use. I have a really funny GIF here that I hope it's not super distracting while I'm talking. Basically, this is the whole Julia installation process. All you have to do is just go to the website, download it, save it on your laptop, and just install it, and like you're ready to use it. So it's a really, if it can fit in a GIF, I'm sure you can get it to work. So yeah, it's really easy to use and quick to learn, actually. And then I'm moving now to some of my favorite components, personally speaking, about Julia. And these are honestly very relevant to my area of research, which is data science and machine learning. So one of the things that is less technical, but to be honest, it's actually very related to why people actually end up staying in Julia, and that is the community. Julia's community is one of the most welcoming communities. And I do have a kind of anecdote here where I say there's no going back after your first JuliaCon. And it's true, like if you go to your first JuliaCon, you just get hooked to the community as a whole. And even online, the communications that happen and the interactions that happen are very welcoming. Going through the rest of my items, one thing I really like is the mathy looking code that is very efficient. Sure, a lot of times we would say like, okay, well, if I want efficiency, I can just go back to C or C++. And this idea of writing something that looks like essentially pseudocode or mathy looking code that is also very efficient is a really key component for me. Julia is also very easy to learn. There are a lot of resources online. One new project that was recently launched is the juliaacademy.com. It has multiple courses on multiple areas of programming. Data science is one of them. There's intro courses, and there's other types of things. I really encourage you to check it out if you're interested in learning it. There's also a growing ecosystem and some really powerful packages. One of them I mentioned here is differentialequations.jl, where all the like there's a lot of components inside that package that are really powerful. I don't think we have the time to go through all of them. One of my favorite is how compostable it is. Like it actually, it's using composability make it sometimes a lot faster. One other component is how easy it is to interface with other programming languages. Basically, Julia is one of the newer programming languages, and we realize that. So basically, you don't want to give up every other package you've ever used in another programming language. So what that means, it is important to be able to interact with other programming languages if you need them. And Julia makes this process really easy. Actually, one of my first experiences with Julia entailed writing a C wrapper for a C package, and it was really a piece of cake. Finally, two last items. It fits right in place. Again, going back to the idea of when I wanted fast code, we can usually go back to C or C++. One cool thing about Julia is when I give someone my Julia code, it's like I've written the most efficient, most like best possible efficiency code. I'm giving them also these new TOML files, which are project.toml and manifest.toml. So like you basically have all of your components in just one place. You don't have to worry about setting up architectures, or you just have everything in one place, and you're ready to just run the code. So it also makes collaboration really easier. I really also like the seamlessness between packages themselves. There's the ecosystem itself for Julia really has like really tremendous opportunities to grow, because the ecosystem itself, the packages within each other, between each other, they talk really nicely to each other. And I really like this idea. And finally, before I wrap up here, I do have some resources for the viewers if they are interested in learning more about Julia. There's the juliaacademy.com. Discourse is a really great place. I know most people ask on Stack Overflow, but in Julia, the community is very, is found in Discord. You can find a lot of questions in Discourse. And I'm sure if you actually ask questions on Stack Overflow, you'll get your questions answered quickly. Also, there's a very active community on Twitter. You can use the hashtag JuliaLang, and JuliaCon is actually online this year. So if you want to go, it's free, and you can get tickets on the juliacon.org. And that's it from my side.
All right. Thanks, Huda. You mentioned community, and I have to say that the Julia community is super active in the chat. Props to Julia for that. Would love to see some of the other languages pipe up as well. And definitely be sure to add your questions in the chat so we can address them in the discussion segment of the event. Next up, representing a little bit of a shift, not a specific programming language, but more the broader idea of probabilistic programming, is Robert Osazuwa Ness. Robert?
Hi. Hi, Sam. Thanks for having me on. So I'm Robert. I run a site called altdeep.ai. I'm a PhD statistician. I came to probabilistic programming by way of causal modeling. During my PhD, I was working on computational systems biology. And computational systems biology is really interesting because there are signal processing mechanisms in systems biology that are inherently stochastic. And so that got me thinking about, how do you build probability into a model, not just to represent uncertainty, but to represent some kind of mechanism inside the model that is stochastic in nature. And so that led me into probabilistic programming. I now work, or I apply probabilistic programming mostly to the NLP domain. And it was actually kind of a natural transition because instead of computational systems biology, it's now computational linguistics. So thinking a lot about kinds of Chomsky's hierarchy, for example, in terms of building a model of language. And this contrasts with some of the more popular deep learning methods, such as transformer networks, where you're really just trying to build a very good model of a conditional probability distribution. That said, probabilistic programming can apply to both modeling techniques. As Sam said, probabilistic programming is not a specific programming language per se, but it's a paradigm for statistical modeling and machine learning that uses a general purpose programming language. So the idea is to use a language to model the data generating process of the thing that of the system that you're trying to model. So this contrasts with the traditional workflow in a scripting language in statistics or in machine learning, where you import some library or package, and then you have some model abstraction that you feed it some data, some parameter settings, and it spits out some artifact or a prediction. In a probabilistic programming language, you build a bespoke model using your host programming language. And so all the languages on this call, I think, except for a few there may be some probabilistic programming languages for a few of these that I'm not aware of, all of these have some PPLs that you can work with. PPLs grew from probabilistic graphical models. You can think of them as an extension of probabilistic graphical models that relaxes a requirement that you have a graph. So just making them Turing complete. So instead of a fixed graph, you now have some control flow. You can use recursion and use all of those programming language, the elements of a general purpose programming language to capture things that you want to express in the process that you're trying to model. And so there's always going to be some abstractions for things like random variables and distributions, and for inference. Chris, I think, mentioned, Chris Nuernberger mentioned metaprogramming. I think one of the more interesting elements of probabilistic programming is the use of metaprogramming to solve inference. So you write your model as a program, and then whatever inference question you have, you write the abstraction for doing that inference as an operation on that program. So we're talking about Julia. Julia has a few probabilistic programming languages. There's Turing.jl, there's Gen.jl. In fact, Julia's composability makes it really easy for you to import your favorite package into the probabilistic program that you write. There's some languages for deep learning, domain-specific languages like Pyro and Edward and ProbTorch from Google. TensorFlow probability from Google. And I personally am very interested in functional programming languages that are, or probabilistic programming languages that are implemented as using functional programming, that particularly when it comes to the metaprogramming problem that I mentioned. I also work a lot on causal probabilistic programming. So in AI, we kind of have this problem right now where causal reasoning is a fundamental part of how humans reason, but our cutting edge models in machine learning don't do that very well. And so I believe personally that causal probabilistic programming has a potential to build agent models that can reason the way humans reason about causality. The drawbacks to probabilistic programming, at least at this stage in its life, is that you have to be good at probabilistic programming, you have to be good at a lot of things. You have to be a domain expert so that you can model the data generating process in the space that you're trying to work in. You have to be able to think generatively and think like a Bayesian. You have to think like a statistician in terms of inference issues, like, is this consistent? Is there bias? What's the trade-off between bias and variation? Is the thing that I'm trying to do even identifiable? And you have to be a bit of a PL person, programming languages expert, because once you remove the graphs from the probabilistic graphical models, you have to start thinking about like the abstract syntax tree of your program and why there might be issues or not be issues with that when you're trying to build your model.
Awesome. Thanks, Robert. That was a great overview of probabilistic programming. Lots of interest in folks expressing interest in checking it out in the chat. Continue to get those questions coming in. Next up, we are going to take a turn to the more traditional side, at least in the machine learning community, with Catherine Nelson representing Python.
Thanks, Sam. It's really great to be here and representing Python. So I interact with Python in a lot of different ways. I write Python code in my day job where I explore new technologies and try and advance machine learning at SAP Concur. I just finished co-authoring an O'Reilly book, Building Machine Learning Pipelines, which is all about putting models in production using the TensorFlow ecosystem. I'm an organizer for Seattle PyLadies, and I was also a speaker at this year's PyCon US talking about privacy-preserving machine learning in Python. But when I think about using Python for machine learning, there's three things that really stand out for me: the frameworks, the flexibility, and the friendliness. The biggest, most popular, and most comprehensive machine learning frameworks, TensorFlow, PyTorch, and scikit-learn, all of these use Python for their front end. And between these, you can go from training your first model to state-of-the-art research to large-scale production systems. And there's a huge number of tools for other machine learning tasks around these core frameworks. To pick a few of my favorites, you can build production retraining pipelines with TensorFlow Extended. You can increase the privacy of your models with TF Encrypted. You can get cutting-edge NLP models from Hugging Face. You can investigate your model with the What If tool from Google. And you have all the tools ready to support your machine learning projects: pandas to manipulate data to get it into your project, matplotlib to plot the results, NumPy to speed up your calculations, and so on. And secondly, Python is a super flexible language and ecosystem. Python isn't just for machine learning, and in fact, most people who are writing Python code aren't doing machine learning. And this means there's a huge ecosystem for data analysis, scientific computing, web development, basically anything that you'd want to do. If you want to integrate with a larger code base, you can just build an API in Python. Last week, I asked the TensorFlow team why they decided to choose Python, and Martin Wick said that having a Python API was a huge advantage for them in 2015. And this meant that the rest of the Python ecosystem was all available for their users. He says that it's really hard to overcome such a powerful ecosystem advantage with features and language, and he doesn't see it changing anytime soon. Thirdly, Python's really friendly, both the language and the community. It's easy to learn, the syntax is quite similar to English, and there's an amazing amount of documentation, tutorials, anything you need to get started. And the community is just really amazing. Senior figures in the Python community still make time for people who are just getting started. Last month, we had Guido van Rossum, Python's creator, as a guest at a panel discussion for Seattle PyLadies. There's lots of efforts to get underrepresented folks involved in open source projects with things like the mentored sprints that happened at PyCon US. And it's truly a global community. Shout out here to PyLadies Ghana, where I've met some awesome ladies and helping get started with data science. And I feel it's a huge benefit to the language to have such a wide community. For me, I feel that Python's superpower is when you want to glue things together, when you want to try things out, to experiment. It's really fast and easy to get started and explore things. That's something that's super important to me in my job. People talk about Python as being slow, but when you're training a model, actually the time-consuming step is the computations that are taking place on your GPU, and that's not being carried out in pure Python. That's taking place in a lower level language anyway. Where Python maybe isn't so great is when you want to serve your model in production and you want the best possible performance. You start to get limited by Python speed and you have the global interpreter lock to deal with. But luckily, there's a lot of tools that will help you use a faster language for serving. For example, both TensorFlow Serving and TorchScript compile your Python code to an intermediate representation, and then they serve it using C++. So as you can tell, I really enjoy using Python for machine learning. It's got all the tools I need, and writing Python code is just fun. Thanks.
Awesome. Awesome. Thanks so much, Catherine. All righty. Next up, representing another traditional language for machine learning is Gabriela de Queiroz, representing R. Gabriela?
Awesome. Yeah, thank you. It's a pleasure to be here with everybody in such, great environment. And it's so important for us to talk about all the languages. And we are so lucky to have all this variety of languages. So my name is Gabriela de Queiroz. I am a machine learning manager at IBM, and I manage a team of open source developers working on open source projects. And we do have internal open source projects that we create, and then we make it available to the community. And we also contribute to open source projects that are external. So for example, we had a TensorFlow committer, PyTorch committer, we have Apache Arrow committer, Apache Spark. So we contribute to several open source projects. So it's very fun to see, like how these languages, they have pros and cons. And I see it as, we as a data scientist and machine learning enthusiasts, it's great for us to have this flexibility. So, and before IBM, I was working for several startups where I was using R in production, doing, also like a lot of like data cleaning. So it was very easy to do in R. There were times where I had to use Python. And then there were times where I even had to use Scala because all the production codes, like our server was running in Scala. So it's fun to see, how can we go from one to the other. But let's go to the R language. So I tried to write down a few points that I think is, what makes the R language so great. So the first one, which I think was very great, that we had this on Julia and also Python, and that goes to R as well. So we have a very supportive community from like all the surveys that were ran by R Consortium and R Studio. What people like the most about the R language is this supportive community. So everybody's welcome. And that's the main thing around R. The other piece is that's very easy to set up and to get started with. So just download, and then you can start using R right away. If you want to use with IDE, like RStudio, it's also like another another piece that you have to download, but then you have everything running like maybe a few minutes. Another piece is, since this is a language that was mainly used by statisticians, and I am a statistician myself, some of the new methods, especially in statistics, are first written in R. Another piece is around reproducible analysis, like how easy it is to set up a reproducible analysis, like how you can make your analysis easy for other people to reproduce. Another plus thing is like you can now combine, or it's easy to combine R and Python in a single data science project. So you can go from one to the other without having any issues, where before you had pretty much to choose one or the other. Another interesting thing that I think is when you are doing code review, like some of the data scientists, they use Python notebook, and using the diff in Git, it's a little bit tricky. Where in R, if you're using the regular R script or the R markdown, it's embedded and easy to do this, to do the code review. Another piece that I wrote is that it's there are very good resources to start and to continue our data science and machine learning journey. So there are several great materials that are very focused in this particular niche, like people, right? So the other piece is like R Shiny. So the R Shiny is in the back end. It's written in JavaScript, if I'm not mistaken. But I don't need to know JavaScript. I can do like create dashboards, interactive dashboards using R. I don't need to know JavaScript. Another plus thing is the tidyverse. So with the release of the whole tidyverse and the ecosystem, now it's much easier for you to go from the data cleaning to data modeling using the same syntax. It's very consistent. It's very easy to understand. It's kind of like reading, right? So reading, it's based on pipes, and you do like this and then this. Another piece is around the RStudio IDE, which is a very good interface, very lovely, very easy to use. You don't need to leave that environment. You can do your R script, you can run, you can either create a blog using a blog down, you can do all the GitHub pull, the push, everything inside RStudio. You can connect to your server, you can create a dashboard. So you can do everything inside this IDE. Another piece that I wrote is that it's a flexible language. So you don't need to be a data scientist to use R. And we see R being used by journalists, by people in health, epidemiologists, and so biologists. So it's very flexible in that sense. That's all my points that I have. I have a bunch of more, but I think this kind of like summarize what makes our language so great.
Awesome. Thanks so much, Gabriela. I really appreciate that you introduced the notion of reproducibility in there. A very important point. Next up, representing Scala, is Avi Bryant. Avi?
Hi, yeah. I like that a few people have brought up, especially Catherine in Python, the difference between what you might use for training a model and then for serving that model or doing what people now call inference, although I find that a confusing term. And then also, I think a bunch of people have mentioned kind of data processing or maybe producing the training data for a model, right? And I think that commonly, languages might have strengths in some of these and weaknesses in others of these. And my first experience with Scala was when I joined Twitter in 2010. And Twitter was starting at that point to use Scala for a lot of their production serving infrastructure, and was also just starting up the ads business and building an ad server that had to be doing machine learning to decide which ads to show. And the production ad server that was doing the inference, the scoring of the models, was in Scala, like most of the kind of new production services at Twitter. But the other parts of the machine learning pipeline were not. So Scala is a good choice for that kind of production serving. It builds on the JVM, which is just an extremely well engineered platform. Is great for kind of long-lived, high-performance services, and they were exploiting that. But for training data generation, for example, Twitter used Hadoop, used Hadoop MapReduce on very large clusters, but they were using either Hive or Pig, which are these kind of SQL-like languages. And what I found actually is that I was the only person on my team that was interested in even learning these languages to be able to put together these data pipelines, and that they also were not very ergonomic for doing really complicated things with. And so I started working on a library called Scalding to build a way of expressing these MapReduce pipelines in Scala, because Scala was kind of the lingua franca inside Twitter. This was before Spark, or rather while Spark was still a research project, but you can think of this as a little bit of a kind of proto-Spark or parallel development to Spark. I found, I was new to Scala while I was doing this, but I found that there were several things about the language that were very valuable for this kind of task, of this kind of distributed large-scale data processing with Scala. One of them is that, again, by being on the JVM, and Scala, like Clojure, has extremely good kind of interop on the JVM. It's very easy to use libraries in the Java ecosystem, and there's not like a high performance cost relative to writing in Java, right? It compiles to very efficient JVM bytecode. And so you get to leverage the JVM, and also the JVM then, as is still true, is very commonly deployed in these kinds of large data processing clusters, whether it's Hadoop or now it might be Spark. And so being able to natively use those clusters is valuable for deployment, right? I also found that the static typing of Scala, in contrast to other languages that actually I'd used before, or in contrast to something like Clojure or Python or the SQL-like languages people were using, was really valuable for these jobs that might run for like 10 or 20 hours, right? That having the compiler actually catch a problem in, you're not taking into account this field might be null in this data or something like that. Before you burn all of this CPU time running it on a cluster is really valuable, and that would actually happen a lot previously to using Scala for this, is that a job would fall over halfway through because of some unexpected edge case in the data, and that the static typing of working in Scala was able to protect us from that a lot of the time. And then the third feature that Scala has is that, as a very functionally flavored language, it has a lot of good ergonomics for building data flows kind of abstractly in a way that can then be captured and planned like a query planner, right? So what I mean is that if you lay out in Scala, I need you to read this data, filter it in this way, map it in this way, reduce it in this way, rather than eagerly doing all of those steps as you would do if you were working in pandas, say, it can build up a graph of what's what needs to be done for the entire job, split it most efficiently into the different steps that are going to be distributed in different ways, or compile it into MapReduce steps or whatever you're doing. And that this kind of reasoning and optimizing of the entire query plan is very valuable for that kind of work. So what we didn't do very much of at Twitter, at least while I was there, was use Scala for training models. And I think that is still an area that Scala is not widely used for, and has a lot of work to do. And one of the things that sort of I've spent a lot of time thinking about is there is no, at least no widespread, no widely used tensor-like library for Scala that you can use to do autodiff and train models on the GPU. And that tensor model, that tensor API that kind of comes from NumPy and then TensorFlow, is really actually quite a poor fit for Scala idiomatically. I think it's a very good fit for something like Python or also Julia, which is used to working with those kind of multi-dimensional arrays. And that kind of multidimensional array and Scala don't mesh very well. And part of that has to do with that same strength of static typing. I think that both as a language and as a community, the idea of having these kind of somewhat amorphous blobs of undifferentiated kind of real values that you maybe have this dynamic shape attached to does not sit well with the language or the kind of idiom. So I did some work towards this when I was at, after I was at Twitter, I was at Stripe for quite a number of years building up data and machine learning teams there. And we also used Scala for serving models, did a lot of work on that, including being able to read models that have been serialized in Onyx format and serve them from the JVM. And also doing that on Hadoop clusters, for batch scoring, and then also using it for all of our ETL. But I did start down the road of what would it look like to build a modeling language in Scala, and built a system called Rainier that's actually, I would call a probabilistic programming system, kind of like what Robert was talking about, that does do a kind of tensor graph autodiff. But it was actually quite challenging to do that in a way that felt good. And we ended up targeting more of a kind of small scale model, Bayesian modeling, rather than the large scale kind of deep learning, very large number of parameters, in part because we didn't have a good way of representing those very large tensors that kind of felt good in the language. But to sort of end on a high note, another thing that we did with the Rainier project that I think was, again, a real strength of Scala is that we were able to generate custom JVM bytecode for the models, compile the models down to extremely efficient JVM operations that would then get just in time compiled by the JVM and would run comparably fast to C++. And that we could do that all in this very easy to deploy, fashion where we just package up a jar and ship it out to these clusters of machines without needing, any other runtime support or anything. And so that ability to sort of go from these very high level functional descriptions in the language right down to bytecode where we're controlling, basically every read and every allocation, all in kind of one cohesive stack rather than having to mix languages like a high level scripting language and then C++ underneath, I think was actually a great strength of Scala for us.
Great. Thanks so much, Avi. And now for the last of our language presentations, we've got Chris Lattner representing Swift. Chris?
Hi, everyone. Great. My name is Chris. I've worked on a number of different things over the years, including compilers like LLVM, MLIR, Clang, things like that. Also, programming languages like Swift. Recently was part of the TensorFlow team where I worked on bringing some of these ideas into the machine learning domain. So instead of talking about syntax and things like that, I thought I would kind of frame how I look at this problem that we're all grappling with to try to propel machine learning forward, and then explain why Swift is relevant and interesting in this space. So I look at machine learning, my view of the machine learning world is that there's a couple of things that are becoming really clear, particularly as it's getting more evolved. Python is the de facto standard that almost everybody uses in the space. I think that's for really good reasons that Catherine laid out, including the great data science ecosystem, the APIs, the mindshare, all this stuff is very clearly true. I think we're also seeing a push towards eager mode. PyTorch and TensorFlow 2 are both moving towards eager mode, and this is really great for usability, debuggability. It just works the right way in a REPL and things like that other people pointed out. On the other hand, Python does have trade-offs. Python isn't really designed for deployment into mobile applications or into high reliability servers. If you want to deploy, then you have to give up a lot of the benefits of eager mode. And so you end up creating graphs, or you end up using subset things that look like Python, but they're not really. Another challenge of Python is that you have another language underneath it to get performance, often C or C++. One of the things I have seen that's challenging is that when you start doing things like reinforcement learning, where you need to pull the trainable part of your model into logic that models the world that you're trying to simulate, For example, you have a board game. AlphaGo Zero is a great example of this. You end up writing a lot of glue code between C, C++, working around the GIL and things like this. And so while Python is really, really great for many of the simple cases, it starts to fray at the edge cases. And so what do we need? In my opinion, what we need is we need a really predictable runtime. We need really good performance. We need good integration with APIs. We need support for mobile and server apps. One of the things I think is really important to this is we can't have garbage collection, because garbage collection with eager mode means that you can't reason about when your tensors get deallocated. And this is one of the subtle brilliant things about Python is it guarantees deallocation of tensors on a GPU, for example, when you let go of the last use. And so you can write reliable, predictable code. You don't get stuck where your garbage collector doesn't run and then you run out of GPU memory. I think we need a system that doesn't regress on a lot of the strengths that Python has, including its huge usability, teachability, the APIs, and things like that. And this is why things like using C++, to me at least, are just not very attractive. I don't think that C++ will be widely accepted as a replacement for Python. So what is Swift? Swift, at a high level, is a modern language. It has many of the nice things that you'd expect from a new language. It's about 10 years old now. It's designed for usability without sacrificing generality. The unique thing about Swift is it's designed to scale from scripting languages and high-level, very abstract programming all the way down to systems programming. And so you can tackle the entire span of programming within one system. Swift has a big ecosystem with millions of programmers. It has packages, workbooks, IDEs, debuggers, all that kind of stuff. It's portable to Linux, Windows, Apple platforms, of course. One of the great things about Swift is that it builds on top of LLVM. And so it has really good interoperability with C, Python, like these kinds of things you can directly use these APIs right from Swift without additional work. A really important and subtle thing about Swift is that it has what's called value semantics, which means that tensors work like math. You don't have to clone your tensors. You can actually write math code and get math results. And as I mentioned before, not having garbage collection is really important. And so Swift provides automatic memory management, but doesn't use garbage collection. So you get that deterministic collection of your tensors. Now, Swift is being pushed into the machine learning space. It also has things like first-class automatic differentiation built right into the language, which is really powerful and great for usability. And there's a whole bunch of things in the Swift ecosystem. But coming back to philosophy, I look at machine learning as a new programming paradigm. And so we've seen many programming paradigms in these languages. You've seen functional programming, you've seen structured programming back in the day, you've seen generic programming. There's lots of ways of tackling problems with strengths and benefits. And I look at machine learning as a really great way of solving certain classes of problems. And just like with functional programming, it's really fantastic for solving certain classes of problems, but you get superpowers when you blend it with you blend functional and object-oriented programming techniques to build a structured application with a UI. And Swift provides that for people. Because Swift can be deployed, it's great for that deployment problem. And so what Swift for machine learning is really doing is providing specific small improvements to Swift language, including things like Python integration, automatic differentiation, integration with specific framework runtimes like TensorFlow and XLA and things like this. And the culture of the community is one that really values API, teachability, and usability. And so it's just a really exciting time in that space. Now, I will say that there is a big challenge that I think that is still being faced right now, which is that an eager mode runtime is really important to really achieve all the benefits of this. And so you really need something like the new runtime that the TensorFlow team is building right now. You need something like the PyTorch runtime that's designed for eager execution. And when you combine something like that together with the benefits of what Swift is bringing, you get a really, really nice system. And that's just coming together right now. So if you're interested in finding out more, you can search for Swift for TensorFlow. That's a great community. They have weekly design meetings. It's a super open and welcoming community. There's lots of videos available, and you can see tech talks and lots of great content from a really interesting new community. So thank you.
Awesome. Thanks so much, Chris. So that marks the end of our structured panelist presentations. Be sure to get those questions in. And if you've not already, while you're there on YouTube, be sure to hit subscribe so you won't miss any of our upcoming programs. And finally, do check out the IBM community at which you can reach via twimlai.com/IBM community. We have had a ton of questions coming in, and the conversations in the chat have been super, super lively. I want to start with a conversation that was actually posted quite a few days ago, actually, on our blog post about this by Joanna Bryson. A lot of the conversation in the chat has talked about combining these different languages and different ideas. And I like the way she put her question. She was curious if any of the panelists find it useful to what she calls anneal their ideas, which she explains as kind of switching between languages to implement the same thing. And if so, what languages do you find really complement each other in this way? Any thoughts on that from the panel? Any takers?
I can hop in. That's actually how I learned machine learning in the first place. I would take an algorithm I was interested in and rewrite it 4 or 5 times in different languages. And the trick is you do that and practice it until the algorithm becomes intuitive and you can start to visualize the space that you're working in. So that approach was really useful for me. I don't use it much anymore in professional practice, but that is how I learned.
All right. Robert?
Yeah, because I'm trained as a statistician, I worked a lot in R, but I working as an engineer, so I work a lot in productionizing machine learning models in Python. Sometimes I found that so when I can't remember who was talking about R. Gabriela was talking about R, and she mentioned the tidyverse and the ability to do kind of line by line piping using tidyverse syntax. And I found that especially when it comes to data munging and again exploratory data analysis, I would start off in R, and then once I understood what it was I was trying to do and I needed to move something into production, then I would switch to Python. I don't know and mostly because I had to switch to Python. I'm not criticizing R as not being production worthy, although I think some people might make that argument.
Chris, did you have something?
Yeah. So Clojure, we have Python bindings, and we actually have really good R bindings that make it look. If you're used to writing Clojure, you can literally import Python libraries as Clojure namespaces and use them directly. And we also have that for R. So we have various ways that from a given project or from a given Docker container, you can just boot up your system and start working with R and Python directly. And there's a marshalling cost for moving data between the various systems, but that marshalling cost, a lot of times that's not your biggest problem. You just want to use some complex tool that, marshalling or otherwise, you want to use it.
Catherine?
Yeah, I'd agree with Burak's point about it being a super great way to learn things. I actually went and tried out the same model in a few of these different languages in preparation for today, and I found that I learned a ton about both different styles of programming, and just working through the machine learning was really educational for me.
Awesome. Chris?
Yeah, I just want to say that I think that a lot of times people get too hung up on the languages and forget that people just want to get things done. And so getting things done, the practical side of it, I think is really important. And if you're trying to solve a machine learning problem, you don't want to go write a new plotting library or something like that, right? And so I've always looked at it as there are really good tools for solving problems, and how do you get the best out of everything? And particularly when you're developing an algorithm, you want to be able to leverage everything. And this is why we've invested in zero cost interoperability with Python, for example, and C and those kinds of languages, because you just want to be able to use that library and be able to take it for granted. And that's really important.
Mm-hmm. We weren't able to cover C++ in a lot of detail here. And a lot of the languages that are represented here, have C++ under the covers when performance is important. We've received a ton of questions related to C++ in general and I'm curious who might have comments on, I'll read some of these questions, but either experiences using C++ directly. Is there a time when you have to switch to C++ or something like Rust in order to be performant in production? There's a couple of questions around C++ and LLVM and MLIR kind of underlying Swift. Curious who has thoughts on C++ at the bottom of all this and performance. Any takers on that? Robert?
Sure, I'll start. I don't have much to add here. I think other people could talk more in depth about this. Personally, when I've developed both Python and R packages, it just became natural to say, okay, well, this is going to be a computationally heavy thing that needs doing. So we're going to have to write it in C or C++. And recently, when I've been thinking about these types of, particularly in inference and Bayesian inference, when I see things that might be a bit expensive computationally, I have been thinking about Rust. So I've been learning Rust, although I haven't yet, as a way of replacing my previous working with C++ to implement expensive algorithms.
Great. Avi, I think you've got a comment here. And while you're at it, there was a question or a couple of comments about the JVM numerical library performance that you might be able to answer while you're at it.
Sure. I think what I was going to say about C++ is that one of the things I really like about working in Scala is that although Scala is quite a high-level language and for a user can often feel a lot like working in more like a scripting language or dynamic language, you don't tend to feel that need to drop down to a lower level language like C++. And if you do write your code carefully, making sure not to have allocations that are going to get garbage collected, because garbage collection, as Chris Lattner pointed out, can be a big issue. Making sure to use unboxed types and so on, you can get performance that is often comparable to C++. And we saw this directly in the Rainier project that I worked on, where what we were benchmarking ourselves against was a probabilistic programming system called Stan that operates by generating C++ code and then compiling that with GCC. And this is kind of a big deployment headache, and we weren't willing to take that on our clusters. But that by generating JVM bytecode instead, we were going to be able to, we were able to get for our models comparable performance, or in some case faster than C++. Now, this question of JVM numerical libraries, I have not seen in Scala. So I guess I should say, you could think of kind of a traditional like on CPU numerical library, right? Like a BLAS. I have not seen on Scala or Java that kind of traditional like matrix numeric library that matches the performance of BLAS or the kind of similar things, right? And typically people would instead link into that. But I think that these days the sort of more relevant question anyway is the on GPU computation, right? Which obviously is not for any of these languages, is not going to be natively in that language. It's going to be a question of somehow producing that GPU code. right? And so at that point, I think, again, probably for any of these languages, you could reasonably produce something efficient. But I do not have experience with using existing Java numerical libraries or Scala numerical libraries. Our experience has always been with very carefully writing code, for the types of models that we were interested in doing, including, generically compiling down a compute graph into very efficient JVM code.
Great, thanks,
Yeah.
Avi.
So when I look at a number of these languages, you have Rust and Julia and Swift. These all compile down into LLVM, and so they can all get effectively full performance of C++. And so with that cluster of languages, I don't think that the performance pros and cons really swing either way. They're all roughly the same performance criteria. I think that what I look at as the advantage of that cluster of languages is that you don't have this two-world problem where you have certain people who feel like they're high-level programmers, and then they maybe should, but don't go down to the next level. They don't want to write that C code, something like that. And so I look at the performance advantage of those kinds of languages as being a huge usability improvement that then broadens the class of people that can participate in that, and it's more inclusive of their ideas. I agree with the comments about acceleration is really important, and so that integration with the runtimes and that integration with GPUs and other accelerators is really important. This is where compiler technology is helpful.
Great. Huda?
Yeah, so I think Chris actually captured a lot of the things I just wanted to say pretty nicely. Yes, these programming languages that actually get compiled down to LLVM code, these already have a very big leverage in that space. But I think the only thing I would add is, again, the way I think about it is also very similar to something that was mentioned earlier, which is you want to get the tools that work for you. And sometimes when you're building a new machinery or even like a programming language or any type of machinery, you want to see what is the existing thing that already existed that is super powerful, and still I want to be able to integrate it in my paradigm. And I feel like being able to actually use existing C code or C++ code that was already written in existing packages and be able to port it into whatever framework you're working on is also very powerful. It goes back to the point that Chris mentioned earlier. You just want to get things done. So if your paradigm makes it really easy to call something that is powerful and already exists, that's also a really added value.
Awesome. And Chris Nuernberger?
Yeah, so on kind of the topic of making things work on GPUs, you can go one step further and make them work on FPGAs, which I'm sure Lattner has experience with. But there is a library that I want to highlight, and it's called TVM. It's TensorVM, and it's the execution model that underlies MXNet. And that's a neat library because you can describe your algorithm, and then after the algorithm description is finished, you can schedule it and transform it such that you can say very specific things, such as compute this partial result and put it onto this multiprocessor on the GPU so that it's in shared memory for all the different threads on exactly that multiprocessor. Or you can basically transform your algorithm in various different ways and compute partial results at various points in your algorithm. And it's a very powerful system for having a single algorithm definition that then you want to transform and place on multiple heterogeneous hardware backends. And I think that is actually a next stage in a lot of these. I can take a for loop and I can run it on a GPU kind of auto compilers. That's very weak as compared to manually managing the shared memory on your GPU correctly, and a lot of the other tricks that people do when they do CUDA programming professionally.
Awesome. Chris, while you're up, we got a question about the availability of scientific computing languages for Clojure for things like linear algebra, time series, machine learning algorithms, etc.
Yep, and I think this folds into the answer for Scala, in that we have a great numerics library in Clojure, and it's called Neanderthal, and it has a backend for OpenCL, it has a backend for CUDA, and it has a backend for Intel's MKL library. We've had many linear algebra libraries on the JVM, and they stand out because he's right. If your bytecode won't do as good as a BLAS library and a matrix multiply, but where they stand out is when you have a matrix that's sparse or when you have matrix that doesn't fit in memory anymore. And then some of these other libraries, which often have the CPU BLAS backing in them, allow you to deal with data sets that are just insanely large or just very, very different. And there's two libraries I want to highlight. One is named Smile. And I kid you not, Smile was written by one person over the last 12 years. And it has like a solid percentage of scikit in terms of the general stuff you might want to do with a new data set. And that's just amazing that somebody could do that. And then there's Shogun, which nobody knows about, but it's a multi-platform kind of machine learning library that, again, is very, very, it's more in the realm of scikit. It has way more algorithms in it, but it has a C++ component that you'll probably have to compile for the specific platform that you want to run on.
Great. So got a couple questions here that I'd like each of you to address in turn. The first relates to kind of our promise for this session that, we'll talk a little bit about, ways that different programming paradigm change the way you think and approach problems. And if you've got an anecdote on that, please do share it. But if so, or if not, there's a great question that was suggested in the chat, and that is, besides the language that you're representing, what second language do you use most frequently? And we'll start with you, Chris Lattner.
In terms of what do I personally use most frequently, probably C++ is what I've written the most of over my career. But I've also used many other languages in many
machine learning.
Oh, for machine learning, Python. It's kind of bimodal in that for me personally. So I think that when it comes to programming paradigms, it really becomes how do you blend them together? And I think that for most programmers, they don't actually really care that much about the syntax, right? Syntax one way or the other. People have opinions, but I don't think that once you've learned that, I don't think that's really what it's about. It's about how do you build, how do you scale, how do you leverage other people's code, how do you deploy, like when you've done your research and you've completed it, do you have to rewrite it to deploy it somewhere, right? And so I think those are the more interesting problems, and that's what the Swift world is focused on. And I think that another really interesting thing to look at is beyond syntax, you can build many things as libraries. And the more that you can build as libraries, the more that it's a user extensible part of the system instead of things that get baked into the world. And this is where I think Julia and Swift are very strongly aligned together. But I think I'd love to see all the diversity in the work and the research being done in the space.
Awesome. Burak?
Sure. So my two languages are JavaScript and PHP. I'm a polyglot. I've worked in a lot of languages over the years, but my company, we do web applications. So why not JavaScript and PHP?
And PHP for machine learning? Anything there?
Absolutely. It's actually pretty excellent for machine learning. Some of the first machine learning I ever did was in PHP. It is an imperative language with object-oriented programming tacked on. So it's not wonderful there, but it's actually very fast. For naive algorithms, right? For naive algorithms, it'll beat Python by, a 3 or 4x margin, right? Again, for naive algorithms, we don't have GPU acceleration in PHP that I'm aware of yet. But in terms of programming language paradigms, I already mentioned that I taught myself machine learning by just writing algorithms in a bunch of different languages. So absolutely the language can help you visualize what you're doing. A simple example, right? Anytime I play with a new language, I write a genetic algorithm. It's just like my favorite toy to write. And in PHP, I write them as object-oriented code. In JavaScript, I write them functionally, right? The first ever neural network I ever wrote was in PHP, and it was an object-oriented neural network. It was small. It was really slow. It could, do basic like face detection for 25 by 25 pixel images, but it worked, right? And building it that way teaches you, it shows you a different face of the neural network, right? You're all of a sudden not thinking about the linear algebra and the partial differential equations, but now you're thinking about what are neurons, how do they interact with the rest of the system, because now you're building an object-oriented paradigm, and you're just looking at the same exact problem from a totally different angle. And I think that's very powerful. It helps you build that intuition you need to be really good at machine learning later on in your career.
Awesome. Avi?
I think the thing that there's a lot of ways in which sort of Scala introduced me to new ways of thinking about things, but I think the one that's been most important from a machine learning context, and Chris Lattner sort of got at this a little bit, is that workflow from kind of research and developing a model to deploying a model to production, and what do you have to do at that stage. And I think that a lot of my career has actually been working on trying to solve that problem and build tooling to solve that problem. So for example, at Stripe, something that we spent a lot of time on was, on the one hand, you've got this code that's going to do kind of backfill of your training data, right? Build your features, from historical data. On the other hand, you've got to have code that is, giving you kind of in some kind of streaming context up to the, millisecond versions of those same features, right? And these are two very different computational contexts, very different goals, but can you have one system that is doing both of those things? And similarly, do you have to rewrite your code between training a model and deploying that model for scoring or inference, right? And so Scala has been an environment that has that kind of flexibility of being both high level enough to do your exploratory work, but also suitable for production, and works in a lot of different computational environments like distributed cluster computing, as well as online stream processing, as well as this kind of low latency serving that has made it work for that. But it doesn't quite have the ecosystem to do the end-to-end, right? So there's a lot of the model training part, at least right now, where it does fall down. So it's not quite there yet, but I can see that promise. In terms of other languages, the language that I'm using a lot right now, as well as Scala, is TypeScript. And yes, including for machine learning. And that one thing that I'm getting really interested in right now is what can you do in terms of interactive feedback while you're doing modeling, right? And how much can we just do in the browser with helping people build models while getting a lot of feedback about the quality of those models. And if you can work directly in the browser's runtime, right, with some combination of TypeScript and maybe WASM and WebGL and so on, then that can be great. There's a lot of challenges to it, but I actually am really enjoying TypeScript as an environment.
Awesome, thanks. Catherine?
Yeah, so the first part about programming paradigms, I appreciate that Python doesn't strongly enforce any one particular paradigm, and this makes it more welcoming and encouraging. It means you're not sort of afraid to try things. You can just get stuck in and start building things. For a second language, when it comes to experimenting and exploring, starting a project, there's no way that you're going to be able to pry me away from Python for that. But like Avi says, when it comes to the training versus serving and inference split, I'm really interested to try out something like Swift or Scala to get the improved performance there. And I also find myself using R for statistics heavy projects because it's all inbuilt there and it's easy to move my data between R and Python.
Great, thank you. Huda?
So I saw something in the chat. Someone said the only problem with Julia is that my colleagues don't use it or haven't taken the time to learn it. So that's honestly the only place where I have, like, if I have a collaborator who really doesn't want to spend time on Julia, that's the only place where I feel like, okay, I must leave to their comfort place. But I do try to advocate, but still sometimes it's hard. But yeah, so mostly it's going to be Python in my case, just because a lot of machine learning people use Python, and it's an older language and has a lot of background. In terms of the anecdote you asked about, again, going back to it goes hand in hand with this question. Again, I try not to leave Julia because I do get my performance out of Julia just as much as I want it to be. Just recently, I think a couple months ago, I was working with a collaborator and they had a C package or a C code that was written, and I needed to use their C code for my project. And I thought I could spend some time writing a wrapper, but I could also spend some time writing the whole code all from the beginning. And it wasn't a really large project. It was a small piece of code. So I thought I'll just rewrite the whole thing in Julia. And yeah, the anecdote there is that this person was very resistant. They thought that there's no way Julia is going to be faster, but it actually was faster. I guess the main thing I would say there is that when you're writing Julia code and you're really wanting to get like the best out of Julia, yeah, there are things you could control, such as memory. You can control how you're accessing memory, how you're storing memory and data. You could think of these things reusing memory, like if you actually use a vector and then you're not going to use it again, you can you don't want to use that variable, you can actually reuse that space in memory. Just you want to keep in mind these separate pieces. And the fact that Julia gives me that power is just amazing. So yeah.
Awesome. Gabriela?
Yeah, so my first languages are, my second language right now it's Python, but in the past was maybe SQL. So I think it depends on like where you are, which company do you work for, what are the language that they are using. Like if they are using R from back to back, from data cleaning to data modern production, your server is running R, everything's running R. So I'll be probably using R all the way. If a company is using Python, the whole infrastructure is using Python, I'm like, okay, I'm going to use Python. So again, I always I try to emphasize that you have to have this flexibility. It's like, I love R, gets me anywhere, like, or everywhere, right? So like I can go from end to end, but like if all my team is using Python, I'll probably have to switch and use Python so we can interact and speak the same language. So that's my key takeaway from like all my experience, and it's what I see in the industry in particular.
Great, thank you. Robert, I'm sure you have a great anecdote about probabilistic programming, because it is quite a paradigm shift relative to some of the other things we've discussed.
Yeah, so, well, for one, like I switch often between R and Python, and then obviously probabilistic programming languages that play with or work within those spaces. So I think what about probabilistic programming, but like most gave me a kind of like aha moments, I say, was in a probabilistic program rather, the each execution of the program is an instance of a random process. So in a regular deterministic program, you have a program, it takes in some inputs. For every set of inputs, it'll give you one fixed execution, right? But in probabilistic programming, you get a whole space of executions, and you're reasoning in a Bayesian sense across that entire space. And specifically, one execution from that space is an instance of a process that generated a data point. And so, when you start talking about program executions and all that, you're really kind of, it's like a computer science course in programming languages, right? Where you're thinking about kind of abstract syntax trees and stuff like that. And then when you start talking about an instance of a random process that generated a data point, you're talking about probability theory and statistics. So kind of having those two worlds come together was kind of an eye opener for me. Most people think about Bayesian machine learning really insofar as, well, I need some representation of uncertainty, but this is going much, much further in terms of reasoning about the system that you're working in. So, for example, if you're modeling something that a person says in a natural language setting, right? Then a single execution of the program is like an instance of a thought process that started with an idea or an intent and then converted into some kind of semantic representation, and then from there transformed into some kind of syntax, some kind of syntax parse, and then from that turned into a thing that comes out of somebody's mouth or that they type in a Twitter message or something like that. And so, and for me, understanding how to think like that actually maps really well to, the times that I've sat down and said like, all right, I'm going to spend a few days just wrapping my head around Scala or Haskell. In fact, Avi, as you mentioned, did some probabilistic programming work, or does some probabilistic programming work. For Scala, if you Google a probabilistic programming language in like 90 lines of code, I think that's it, by Darren Wilkinson, who's a statistician and computational biologist in the UK. Can't remember which university. He'll, kind of using, it'll show you how using kind of basic ideas from probabilistic, from functional programming, you can implement a probabilistic programming language. And I think that it's a weekend exercise, well, maybe longer if you're not familiar with functional programming, but it's the kind of thing that it's the kind of exercise that, you really kind of take a whole bunch of completely separate domains of research and reasoning and engineering and kind of connects it all together in one very coherent way of thinking. And it's been transformational for me in terms of, well, everything, my career especially.
Awesome. And Chris?
Yeah, so I'm going to keep this fairly short in terms of, I've learned a lot from Clojure. I could go on forever about it. The thing that is striking about a Clojure project is its simplicity. There's a lot of meaningful things done in Clojure that are 50 lines or less, and they're libraries that are incredibly useful. And you just have it's hard to explain to people how concise. Functional programming is generally pretty concise, and Clojure is a very concise functional program. So you have a lot of compression of code there. And there's two languages that I want to give a shout out to. And the first is honestly Julia. I think Julia would be a great partner for Clojure. I tried to embed Julia, but there are actual problems with the way that Julia handles stack frames and the way that JVM handles stack frames, low-level things that I don't have the time right now to go after.
I'm sure a lot of people would love to talk to you about this, and we can talk offline. And
please, by all means.
Yeah. Cool.
And the other thing I want to say with a little bit more perspective, I think a language that is not represented here that should be is APL, and the class of languages based off APL. When you guys are using NumPy, or when you're using a lot of things in Julia, a lot of these concepts came from APL. And when you're programming GPUs, you actually can use array-based programming concepts on a GPU really, really well. And so the language that I think is the most compelling, and you can see this in the work that I've done because it underlies our entire machine learning system, is for me the basis of array-based programming and how it mixes with whether you have a garbage collector or not in various languages.
Shout out to languages that require their own keyboard.
Absolutely.
Oh, that's not fair anymore. So APL is maybe the most extreme of compression, but there are APL-derived languages that now don't require their own keyboard and have all the advantages that Chris was talking about.
That's awesome. Well, this has been an amazing session. We've got a ton of questions, and we were not able to, barely scratch the surface on them. But unfortunately, alas, we are going to have to wrap up. The recording of today's session will be available on YouTube immediately, I believe. So please be sure to share it with your friends. A big thank you to everyone who tuned in, and a huge shout out to our fantastic panelists, all of you, for joining us today. To stay up to date on our next session, of course, visit twimlai.com and sign up for the newsletter, twimlai.com/newsletter. And of course, follow us on Twitter at TWIML AI. We will also have a page on our site for this session, and it'll have links to the Twitter handles and the like for all of our panelists, so you can easily follow them as well, which I encourage. Once again, a shout out to IBM for their support in making this discussion series possible. IBM is committed to educating and supporting data scientists and bringing them together to overcome technical, societal, and career challenges. I strongly encourage you to check out their data science community site, which you can reach via twimlai.com/IBM community. Thanks so much, everyone, for tuning in, and we will catch you next time.
Thank you for organizing this.
Yeah, thank you very much. This was amazing.